Our next speaker, Wolfram Schulte, is here at Microsoft, actually. He's an author whose work has often appeared in IEEE software. And he was also the guest editor who helped us put out an issue, I think in 2011, right, on parallelism on the desktop. Okay. At Microsoft, he's currently leading what sounds like a very exciting team, an advanced development team called Tools for Software Engineers, which represents a collaboration between product teams here at Microsoft and folks from Microsoft Research as well. Prior to that, he founded and led for a while the Research and Software Engineering group at Microsoft Research. So, Wolfram?
Yeah. Hello, everyone. Oh, is the microphone turned on? Okay, let's try that again. Hello, everyone. Good morning. I hope you're enjoying, you have some time to enjoy Washington State. We don't have always this nice weather. But let's talk a little bit about my current challenge. My current challenge is, in some sense, to improve the developer productivity. And in order to do that, why not use, in some sense, the exhaust of the engineering process at Microsoft? So what I want to tell you is a little bit about the story, about what kind of data we are collecting and what we can do with it in order to help, in some sense, people in the field. So you're all software engineers, but I thought I'll put this up because it's a nice reflection of what's actually all about, all our optimization efforts. So this is what is Somerville's 9th edition of software engineering, and it simply says, produce high-quality software with a finite amount of resources to a predicted schedule. That hasn't been changed for the last 20 years. And in fact, it's actually very similar to any other manufacturing as well, because what you have to optimize is, in some sense, the quality of the product and the time available to produce it with minimizing cost. And maybe you can play with cost, maybe you can play with quality, we can play with time, but getting the right balance is really key to be successful. Okay, so if this is software engineers, then in order to optimize this, we need information. And we look at different roles, and actually different people need different kind of information. So the engineers that are sitting in the field and are working on the code that really want to know is, how does the code work? Where are the bugs? What are dependencies? Or what are other people that have been working on the code? On the other hand, the managers, they want to know is, how should I actually structure the development process? What's the quality of the product at the present time and maybe 3 months down the road? Can we ship on time so that we hit, in some sense, the product that it gets out before the holidays? How can we set up an organization? Do we have actually the right proportion of testers and developers? And ultimately is, how do the customers react to what we produce? So there's very different information needs, and Aisha already pointed out that there are lots of different places where this information comes from. I will come back there later and talk first about analytics and what we can do about it. So analytics and software engineering is probably relatively new, but in some sense in the business world it exists for a long time. And so this is one of the later books on analytics at work. And I'll just add software engineering to it. So it's use of software engineering data, analysis and systematic reasoning to inform and make decisions. And what is very nice in this book is something that I think we often forget. There are many ways of using analytics. And so I report on a table that's in this book. So you really want to look at what happened in the past. And just sometimes it's good enough to know is, oh, this has happened. Maybe we see is what the churn rate was. More important, what is happening now? If we could get an information, there are 2 people changing the same file. Why do we wait 3 weeks before that file is being checked in? We should, in some sense, let them know right away what is happening now. So doing alerting. Or what will happen in the future if they don't fix it now. And then there's insight. That's really what, in some sense, the analytics community is all about and excited about. But then it's not only machine learning, it's also modeling how and why did certain things happen, and how can we predict what will then happen in the future. So with this, I want to show you in some sense, we use in some sense all of these techniques in order to optimize development processes. And one thing that is in some sense very important if you want to optimize for time is figuring out how does code move through the development process. And so I will talk about branch analytics here. So since you're all software developer, you all use some source control management system. And why is that really important to use that one? Because you have to have a history, and you really want to coordinate the work of hundreds. For Windows or Office, it's actually thousands of developers at the same time. And what you typically do is, what you often do, Microsoft has done in the past, is in some sense introduce a branching structure in the source control management system. And so what the benefit of the branches are, that they individual groups that work on Media Center or IE can work in independent. So you separate them out, they can make independent progress. But then you have in some sense the problem that you have to merge everything back. And so there is in some sense your cost. So you really, it's an optimizing problem where you try to enable the developers to work as fast as possible without, but always paying the price of getting things back into the system. And so how can you visualize that? So since we are monitoring lots of source depots and version control systems, we simply say, let's actually correlate the branches, the flow, velocity on volume, and visualize it. And here is a graph that in some sense where the nodes are the different branches. And normally we would actually, since it's not meaningful here, we would say, so the size of the nodes are the number of developers working in this branch, and the edges are the flow of the code. And now, with just being reporting, just looking at that data, you see is, oh, maybe there's actually one particular branch that's really slow. And why is that so slow that in some sense changes from that branch? Slow means here there's in some sense a red edge. Why does it mean that it's actually so slow that it gets to main? And so if you look into, let's say, 10 years back, then there were many product groups inside Microsoft, outside Microsoft, which needed days to integrate stuff back into main. Google, another company, says, okay, let's get rid of all the branches. We always work in one branch. But that has also its problems. So it's really what you want to do is optimize the whole system for maximal flow through the system. And so what you want to do is seeing whether you have one, in some sense, branch structure, and you want to move it to another branch structure in order to optimize the flow of code through the system and isolating the developers so that they can work independently. Now the question is, how do you get from A to B? The good news is we have all the data in our version control system. So what we can do is we can simply take a branch out and simulate now, in some sense, run the history of all the check-ins and simulate what would happen if that branch wouldn't exist. Would there be more merge conflicts? Would the code actually move much faster through the system, and so on? And we can measure in some sense and evaluate what's the impact on velocity, so on code flow, and on conflicts. And then we can simply identify those branches that are in some sense have a high velocity cost because they only add process, but they don't help developers, and then we can take them out. And so this is in some sense what happened from the left to the right. We ran in some sense a simulation of the past where we simulated a different future, and this new different future looked better, and then we said, okay, for the next version of the product, we use then this new branch structure. And so what were the results? That actually 35% of the code flows faster through the system from a developer check-in in one branch until it hits main. So it means is other people can rely much earlier on it. So we wanted to optimize for time. That's great. But then something else has happened is because now we actually analyzed, in some sense, the branch structure to minimize the number of merge conflicts. There were actually much fewer merge conflicts. And these merge conflicts typically stop the whole development process because nobody can continue checking in because something is broken. And so in the end, we get even a better reliability. And now that we have actually fewer branches that we have to build and maintain, we have fewer hardware costs. So we wanted to optimize one thing that was really time. And the good news is we actually got the benefit of 2 other aspects as well. So this was in some sense optimizing time. Let's see whether we can actually optimize something on quality as well, and whether we can actually play with both ones. And how risky is that to play with the interplay between quality and time. So what we wanted to do is actually see when people check something in, can we predict whether the thing that they checked in will be risky? And risky, so how can we define risky? In some sense, risky means you know that you have to fix it in the future. So that's in some sense the challenge that we had. And so how can we get there? We can actually see because most of our products are developed in versions, we can go back one version in the past and see what were the changes and what were the resulting bugs. And we can use this as a model in order to train the system for what is currently going on in the field. So that means we have, in some sense, a version N development, whether it's Office 13 or Windows 7. We can look in the number of post-release bugs. We can correlate them back to when were they actually introduced in the development. We can build a model, a predictor. Now we can use that model, and whenever the version N+1 development happens for Windows 8 or Office 15, we can apply this model for the next version that we trained in the past in order to predict what happens. So how does that work? So the metrics that we're actually using for these predictions are in some sense all the metrics that we use in software, in empirical software engineering all the time. So simple things like code metrics. Somebody checks in something that seems to be really complicated. Maybe we should be more aware. Code churn. If there was lots of churn on this code, that's also not a good sign. The number of bugs that have been reported in the past on it. Ownership. If this is in some sense somebody who checks in something again and again, and he owns this code, it's likely that it's actually okay. Whereas if it's a minor contributor that checks something in, that's actually a little bit dangerous. The developer experience. If it's somebody who comes in some sense like fresh with a bachelor and just does his first check-in, that's more scary than if it's an experienced developer that worked in the kernel for 20 years. And so we take those metrics and then we build a logistic regression model, and we give probabilities of, in some sense, the risks. And so what do we do with these probabilities? We give them now back to engineers as one thing and the managers as other, because they want to see different things. What does the engineer want to know is, if he does a code review, he wants to know how serious should I take this code review? Who has actually worked on this code? How likely is it that in some sense something will break? And depending on the risk, we can now say, maybe from the past experience, here is the next guy who actually worked, who owned this code. Maybe that's the person that should be actually on this code review. So we use the risk information in order to pre-select in some sense possible reviewers, as well as make the reviewers aware of that check-in. Then the manager gets a different dashboard. He wants to optimize the resources, and he wants to have a quick overview of, in some sense, what's all the risk of the churn that comes in. And so both are, in some sense, enabled with this additional information to hopefully make smarter decisions. But we don't recommend actions. Not yet. This is, in some sense, putting the human back in the loop, as Aisha said. So now the question is, can we even be more vigilant and trading time for quality? And again, let's use some of the data and see what we can do. So what's the principle of test prioritization? So if you have, in some sense, huge test suites, and Microsoft has test suites that are often several times bigger than the product code, then they run for minutes, days, weeks sometimes. And so you don't, with each check-in, you can't run all the tests all the time. But what happens in principle is that the more tests you run, you get, in some sense, more bugs you find. So the question is, can you actually select tests wisely so that with fewer tests, you can actually find bugs faster? And so what we can do is, in some sense, use again the information that is in our system in order to prioritize those tests that most likely find the bugs faster. And so what the principle of test prioritization is, then simply to go to the right-hand bar. That's, in some sense, the graph that we want, where we find the bugs faster. So the number of bugs is on the horizontal scale, and the jobs executed on the x-axis, and the other one on the y-axis. That we want to, in some sense, see is, we only execute a certain percentage of tests in order to get a certain kind of effectiveness of finding bugs. So that's, in some sense, the test selection. And we would like to know is, how can we actually get from the left graph to the right graph, and where should we draw the yellow line so that we only execute a certain amount of tests in order to find bugs. And so what the idea that we came up with is, in some sense, drive this from risk and from coverage. So how does it work for coverage? Suppose that you have, in some sense, a program that's split into a set of blocks, and there are, in some sense, a whole set of impacted blocks by the change. And we have a given set of test suites, and the tests are here labeled T1 to T5. We don't want to execute all 5. We want to execute as few as possible. So we know from past runs that if we run test 1, that in some sense, it will, in some sense, cover 5 out of the 7 blocks that are being impacted. And so we can give them simply weights. If we then say, OK, let's take test 1 and add that to our test set, then we see is what's the next possible best coverage that we can get by running the other test. And we see if we run test 2, then we get, in some sense, cover exactly the 2 ones that were still missing. And so the test set 1 that consists of test 1 and test 2 is perfect because it covers the whole impacted block. So why should we actually execute all 5 tests if only 2 tests already cover, in some sense, our change code? But we can say, OK, depending on how far you want to go, maybe we should actually have another test set. And so we can now go through the other tests and see how much they are covering. And then you would see is that T3 covers already 4. And you have to, in some sense, add one more test to the test set 2 so that you can get to a test set that, again, is covering, and so on. And so what you see is that there are, in some sense, 3 test sets with different capabilities of detecting some things. But running test set 1 is actually sufficient. So if we do this and evaluate it on, in some sense, massive scale for Microsoft by running side-by-side experiments, we recognize that, in some sense, with 10%, you almost get 70%. 10% of the tests, you almost get 70% of the effectiveness of the existing test suite. With 20%, you're at 75%, and so on. So that means why should we actually ever run all 100% of our tests? What the team decided is that they said is, OK, we really want to have fast turnaround. So after a check-in, we want to have, in some sense, the right test run really quickly. And so the daily tests are actually now using this algorithm with, in some sense, very good bug detection rate. And then in order to trade, not really trade quality, they simply said, okay, on the weekend we run then all the other tests which give us the 100% bug detection rate that, of this particular test suite. And again, by doing that, there were lots of infrastructure savings. And if you look at the scale of Microsoft, it's typically in the thousands of machines and maybe in the hundreds of man years that can be done with those techniques. Okay, so how do we get there? One thing is we don't have, in some sense, big data like Twitter, but we have lots of data. And we have lots of data in various different formats. So we use different version control systems. We have different bug repositories. And so one thing that we came up with is that is in order to have tools that work across the company, across different technology stacks, you need, in some sense, some federation of data and some master schema for the data that collects all the meta information about the sources, but in a unified format. And so the tool that we developed is, or the database is called CODEMINE, and we are monitoring approximately 100 repositories for Microsoft with a reasonable amount of data and with many active users and more so tools. And in order to give you the spectrum, we really wanted to, in some sense, we started with the engineering data. So this is really the source code, the changes, the integrations, how the dependencies are. We have added, in some sense, people data is very important because you want to know ownership, how long is that person in the company to make an assessment. You want to know is what are they working on, features and defects, how to correlate it back to the churn. What are the code reviews that they have submitted, and what are the comments on it? And then we have, in some sense, something else that's very important is because we have different speaks in Microsoft. What's a milestone? You have to understand, in some sense, the vocabulary that people use inside Microsoft and their schedules. So there's process information, how the source code came to existence, when it was shipped, created, and so on. And then you go more into the operational part where you actually speak about builds, test, and deployment. So in order to correlate bugs in the field back to the check-ins and the review that was done on those. And so we have three scenarios that drive then, in terms of the use of this monster database. It's in some sense for special purpose tools where in some sense users don't see that there is this database sitting underneath. I've just shown you the branch optimization, risk analysis, test prioritization. But then it's also being used to just drive dashboards, as we have seen, dashboards for business groups for churn, risk, bugs, ownership, velocity, build stability, and all this other stuff. And then it comes along that everybody has his own particular question. Are we moving from unmanaged to managed code, and how fast? How long does it take that people actually, until people check in their first thing after they've joined an organization? How likely is it that the thing will break because there are two people currently working on something like this? So there's lots of one-off queries where engineers just want to understand how the system works. And while building this system, we actually came across several things. One thing is Microsoft is diverse, but in order to have tools for everyone, you have to get to a uniform schema. Otherwise, it doesn't work. Otherwise, you build one tool again and again and can never harvest. In some sense, you might have local optima, but not. But it's global sub-optimum. You need, in some sense, the uniform representation. But at the same time, everybody wants to own his data and has special policies for the data. So you have to provide uniform representation and individual instances that can be replicated because not everything is on the campus. Maybe something is in India and so on. Encoding the process information, we didn't have that immediately, initially. And so it was in some sense an enabler that we finally can speak the same language as the engineers. you'll never be perfect with all the data you are collecting, so you always have to be aware that you have to be able to federate data access because they have their own special information that they want to store. And then we spoke already about discoverability. So the last line was engineering data is a gold mine. It's really literally a gold mine because we can optimize our processes so dramatically if we actually exploit that data that we are already collecting for process practice and tool improvement. Well, with this, I want to conclude. While I lead a team, I think I couldn't do it without, in some sense, the people that are actually doing the work, and that's the insights were provided by these famous people. Thanks so much, and I'm happy to take questions.